Hello everyone. So today we will learn about a new algorithm known as Convolutional Neural Network or the CNNs, or also acronymed as ConvNet. The advancements in the computer vision area with deep learning has been constructed and perfected in time primarily over one algorithm, and that is this algorithm, CNN. It's no doubt a very important algorithm in the deep learning area. Let's try to understand the basic maths intuition behind it, and then we will move on to the Python code of it. Moving on, here this figure represents a basic roadmap of the CNN algorithm. That is how the CNN algorithm proceeds. So first, an input is taken. In CNN, the input is always an image. An input is taken, and generally we have to classify the image input according to certain classes in some classes. So this image is taken, and the various, and suppose we are taking only this particular part of this image. So this particular part is passed through multiple layers. The first layer comprises of convolution and ReLU. So convolution is a particular process in the CNN algorithm in which the image is reduced to a matrix of pixels, which helps in performing the further calculations very easily. After convolution and applying ReLU, we move on to the pooling. Then we again get a matrix upon which we again apply convolution and ReLU, and finally this particular chain repeats again and again till we get a final matrix, and out of which we flatten the matrix, and after that we get a fully connected ANN type structure. Processing that ANN structure and applying different activations functions, we finally are able to classify that image. So this part is of feature learning, this part is of classification, as simple as that. Now in CNN there are many filters. CNN is not restricted to one filter. The first filters that you apply are generally used to segment out the light features such as edge detection and gradient detection, etc. As more and more features are applied, the more complex features are filtered out. So a convolutional neural network is a deep learning algorithm which can take in an input image, assign some importance, that is learnable weights and biases, to the various aspects or parts in the image, and by this process is able to differentiate it from one another. One important advantage of convolutional neural network over other deep learning algorithms is that the pre-processing required in it is much lower as compared to other classification algorithms. So let us write the advantages. So the first advantage is much less pre-processing is required. Let's move further. The architecture of a convolutional neural network or a ConvNet is analogous to the connectivity patterns of the neurons in our human brain, and you would be surprised to know that the organization is inspired by the neurons of our visual sensory organs. That is, you might know that the neurons in our brain respond to the stimuli only in a restricted region of the visual field known as a receptive field. And somewhat similar actions also take place in the convolution neural network. Now there might be a question. Why convolutional networks over a feed forward, okay, just excuse me, over a feed forward neural network? So there might be a question that why aren't we using this for classifying images? Now you may know that when an image is converted into matrix, it looks somewhat like this, kind of square or rectangle matrix. Now for my case, I'm just considering a square matrix, and let the values be 1 1 0 4 2 1 0 2 1. Now this is our image matrix. So to proceed on with it with a feed forward neural network, as we did in case of ANNs, we need to have a flattened matrix. So flattening it would look somewhat like this. One one zero four 2 1 0 2 1, and then hence you would feed it to individual neurons, which would proceed like in the normal ANN process after assigning weights and biases. So it may look viable, right? But this process has been tried and tested, and it has been seen that the average precision score while performing the prediction of classes through this method will have little or very negligible accuracy, as in the matrix form, the different pixel dependencies that we have contribute to the different aspects in the image. A convolution neural network is able to successfully capture the spatial and temporal dependencies in an image through the application of relevant filter. The architecture performs a better fitting to the image dataset due to the reduction in the number of parameters involved and the reusability of weights. So let us dive deep into this process. So the role of convolutional networks is to reduce the images into a form which is easier to process without losing features that are critical in getting a good prediction. Now, we must remember that a good architecture is not only an good architecture which is good at learning features, but is also scalable to massive data sets. That is, you must be able to scale it. Coming to different parts of this convolution neural network, the first part that we would learn is the kernel or the filter. So this is a very important part in the convolutional neural network. Consider my image to be like this. So I would be considering a 5 cross 5 1 2 3 4 5 matrix. Excuse me for the imperfections in my drawing. So 1 1 1 0 0 0 1 1 1 0 0 0 1 1 1 0 0 1 1 0 0 1 1 0 0. So we have a black and white image, and that somewhat looks like this. Now our image dimensions, let us write the image dimensions. 5, which is the height, cross 5, which is the breadth, cross 1, number of channels. So we are considering only one channel of this image. So in this demonstration, this entire section resembles a 5 cross 5 cross 1 input image. Okay. Now the element which is involved in carrying out the convolution operation, you must be remembering the convolution operation from here. Let me just move to the diagram. See the convolution operation. So the thing that is involved in this convolution operation is the kernel. So first let us define a kernel. So let the kernel K be simple matrix, a 3 cross 3 matrix, now what happens in this convolution operation is this kernel, suppose this like I'm just showing it to you, that this kernel strides on this entire image for each and every particular row and column. Example, that first the kernel will, suppose the kernel is moving on this particular section. Okay, so the kernel is first taking on this particular section. Then suppose this particular subset of the matrix, I'm just defining it to be I1. So I1 would be multiplied with K. Okay, so I1 would be multiplied by K, matrix multiplication, simple matrix multiplication, and there would be some particular result. So in this case, like suppose the result is 4. Okay, I think it's also like practically is also 4, because 1 into 1 plus 1 into 0 plus 1 into 1 plus here we have this entire thing like so 2 and there we have it 1, so 1 here, 3, and then here we have 4. Yeah, so it's 4. So if we multiply our I1 with K, we get 4. Then consider this matrix. We name it as I2. Now I2 into K is 3, and so on, like just moving one block, like this entire this subset taking would shift only by one block, and the kernel would be multiplying with each of the subsets. and a corresponding convolved matrix would be formed, which would be somewhat like this. Here the dimension is 5 plus 5 plus 1, and here the dimension would be 3 cross 3. How? Okay, so first let me write the values. 4 3 4 2 4 3 2 3 4. Okay, so this value corresponds to this I1, this 3 corresponds to this I2, and finally this corresponds to this, like this I3. Now after that there is no move to just for the kernel to stride on, and hence this is my last column. Similarly, now after that it will just move on like this. It will take this will be my I4, and hence I get 2. Similarly it will move and continue, and until and unless this entire thing is covered, it will just go on. So in total the kernel shifts 9 times to make this convolved feature. This is known as convolved feature. Okay, so here my stride length is 1. Note that you can always change this stride length according to your needs, but in this case I don't have any other options other than 1. Well, we had an option. If we did stride length equals 2, in that case instead of a 3 cross 3 matrix you would be getting a 2 cross 2 matrix. So that is also one type of convolved feature, but with a stride length of 2. Okay, so the filter moves to the right with a certain stride length till it completes this entire width. Entire width it would be covering. That is the entire image it would be covering. Now we must remember that in a image, in a full colorized image, there are 3 channels, right? So to obtain a fully colorized convolved feature, we need to do this convolution feature for each of this channel. Convolution feature, not feature exactly, that's operation. For each of the channels, and after that you will be getting a full-fledged convolutional image. Okay, now in case of images with multiple channels, like in case of RGB images, the kernel has same depth as that of the input image. That is, it would look somewhat like this. That is, it would look somewhat like, suppose this is your, like I'm trying to show it in 3D. It would not be perfect, still you can understand it. Like suppose these are my 3 channels that's going on, and my kernel would somewhat look like, just wait a minute, like these are my rows. Okay, and my kernel would somewhat, okay, just let me complete it. Yeah, so my kernel would somewhat look like taking this entire block thing. Okay, taking this entire block thing, covering this entire thing, it would be somewhat like this. Okay, just try to visualize it in your mind. A cube-like structure, kernel, that will just move on to cover this entire 3D image. Alright, so the objective of the convolutional operation is to extract is to extract the highest level features. Like for example, I'm just giving edges. Like you need to identify the edges very clearly in order for of object classification. So, but you must remember that convolutional neural networks need not be limited to only one convolutional layer. Now, conventionally, the first convolutional layer is responsible for capturing the low-level feature, but with added layers, the architecture can always update to high-level features and thus giving a wholesome understanding of the images in the dataset. Now, there are two types of result to this convolutional operation. One in which the convolved feature is of reduced dimensionality, and another is the dimensionality either increases or remains the same. Now you know that this first thing, that is the convolved features of reduced dimensionality, is not much preferred. This is not much preferred. The reason is why that if you reduce the dimensionality, that would somehow in some way or the other correspond to loss of information. But if you try to keep the dimensionality as same, that would significantly reduce the information loss in the longer run. So how that thing is done? That thing is done by a process known as padding. Now, padding is a very simple process. Let me show it to you. Basically, the 5x5x1 image that we have shown it. Now, what if we just augment it to a 6x6x1 image? Okay. Now, let think of a hypothetical situation in which our 5x5x1 image is augmented to a 6x6x1 image. Then if we convolve this, and after convolving this, we would get a convolved matrix of dimension 5x5x1. Okay, like after convolving with 3x3x1 kernel that we were doing previously, we would be getting a convolved matrix of dimension 5x5x1. Now, how to do this such that the information loss is minimized? That is, we have to increase the dimension of this 5x5x1 image, and also you have to take precautions that no additional information or the information is not distorted in any way. Now, this is done by generally by adding a blank layer on all the sides. Suppose this is my matrix. If I add one layer here, add another layer here, add another layer here, and a layer here. Okay, that is, it will be somewhat looking like this. Suppose we are having the 1, 2, 3, 4, 5, and this one 6, and in the outer layer that we just added right now, the image would be the not image, in the numbers that would be there in this blocks would be 0, 0, like it would be all 0. They all would be 0. That is, they don't convey any additional information. They are only acting as a padded blank layer such that we are helped with this convolving, such that after convolving with a 3 cross 3 cross 1 matrix, we get a convolve matrix of dimension 5 cross 5 cross 1. Okay, so this type of padding is known as same padding. All right. Okay, so let's move on to the Python code. As you can see here, we have first installed the pip keras tuner, that is the keras tuner library. It's a very useful library, and it basically contains all the hyperparameter tuning that we could do in any deep learning application. Okay, so let's move on. Then I've just imported my regular libraries from, that is, import TensorFlow STF from TensorFlow, import keras, import numpy snp. Now I just took a dataset fashion underscore mnist. This fashion underscore mnist basically consists of different objects of like fashion items, like basically clothes and shirts, t-shirts, like this. So fashion underscore mnist equal to keras dot datasets dot fashion underscore mnist. Then train images, train labels, test images, test labels equals to fashion underscore mnist load. Now this is a inbuilt dataset of the Google Colab, and I did not explicitly as such download this dataset. And one advantage that basically comes with this sort of inbuilt datasets is that the train images and the train labels, test images and test levels are explicitly mentioned in this kind of things. So I don't have to like implicitly mentioned, basically I'm wrong in my terminology, and implicitly mentioned, so that I don't have to explicitly mention them while loading. Okay, so the first thing that I do is train underscore images equal to train underscore images divided by 255. Now I divide the images by 255. Now what benefit does it do to me? If I scale down the images, like each pixel I'm just scaling it down, then although the essence of the pixels is kept, but the size of the image is reduced to a lot. And since we have to deal with lots and lots of images, so it's better if we keep our image size small, like as much as possible. Then I just took the first image of my train images, and I just printed out the shape. It's coming out to be 28 cross 28. Fine. Now I need a proper 3-dimensional image, so I reshape it into 28 cross 28 cross 1. The same I did with test images also. Now I'm just building my model. Now look into it very carefully. I defined a function. Within that, like I'm just first giving an overview, then I will just move on to the details. Now within that, what I did is I created 2 convolution layers, one flattening layer and the next output layer. You can just correlate with this diagram if you all just remember. Okay, let me just show the diagram again. Yeah, so this diagram basically I'm talking about. So this entire this feature learning part, which is which is in this Python code, it comprises of these 2 blocks. So this happens here, and then it comes my flattening part, then the softmax part. Okay, that's the output layer. Now I have mentioned it previously also that I need not only give one convolution layer for my entire model. Many convolution layers I can also like define it and use it. Like it would be according to my choice that how many convolution layers I will put into my model. So let's start with it. So model equals to keras to sequential. Now in any sequential type of deep learning model where one thing follows the another in a sequential pattern, we use keras sequential. So within that, keras layers convolutional 2D. So here filters equal to hp.end convolution 1 filter, minimum values 32, max values 128, step 16. So this line basically defines my kernel. Now the kernel that I use for convolution. So I named it as convolution 1 filter, and the min value is 32, max value is 128. That is, the values in the kernel can be anything between 32 to 128 with a step of 16. Okay, so now after I define the values inside the kernel size can be either 3 cross 3 or 5 cross 5. That's why hp.choice is given instead of hp.end. Now the activation function that's kept is ReLU. Input shape is 28 cross 28 cross 1. The same thing is done in the second convolution layer. That is, the identical convolution layers are created. Finally, the flattened layer, layers.flatten, layers.flatten, and then layers.dense units equal to hp.int dense 1 units, minimum 32, maximum 128, step 16, activation value. That is, this is basically the this flattened layer being carried out. Okay. Okay, so like then comes the final output layer, and that uses activation of softmax, and with like 10 output neurons. Now after that, I will just like I define my model entirely, and I just I now compile this entire thing. Now model.compile optimizer equal to keras.optimizer.atom. There is the atom optimizer. Now there are many optimizers to it, like stochastic gradient descent and many others are there, but it has been but using atom is a very good choice because it most of the times it gives a good accuracy. Okay, so I use the atom optimizer, and within that my learning rate can be anything between 10 to the power minus 2 and 10 to the power minus 3, as can be seen here. So that's the learning rate. My loss is sparse categorical cross entropy, and the metrics that I'm taking is accuracy. I hope you're not having any doubt in this part. Now I'm just returning my model. Now then, from keras import random search, from keras.engine.hyperparameters import hyperparameters. Now, as you might be guessing, we are just proceeding on to hyperparameter optimization. Now, tuner search equal to random search, build model, objective equal to val accuracy, max tracks equals 5, directory output, project name, MNIs to fashion. So this is like I just want to keep my outputs in an organized manner that corresponding to each image that will be classified into any one particular class that will be kept in a particular directory called output inside a project name of MNIs to fashion. And this build model is just called here. And my objective is value accuracy that we just considering. Okay, so now next just coming from it, tuner search train images test train levels epochs equal to 3, validation spirit equals to 0.1. So with 3 epochs and a validation spirit of 0.1, I'm just training my model here. Now after I finish my training of the model equal to tuner_search.get best models. So I'm just like trying to find out my best model, and I initialized into a variable known as model. Now let's see the summary of that model. So in this summary, like I'm just if I do model.summary, I will just get out the entire details of that particular model. So layer type, first convolutional layer, convolutional 2D layer, and that is like the number of parameters, the total number of parameters in it is 640. Okay, and like it's 26 cross 26 cross 64. 64 means this value that is taken basically is 64. Okay, so now in the next part, the convolution 2D_1, and the total number of parameters is 76848. In the flattened dense 1, and as seen, total parameters 1 and 936, 938, and so the model basically is like the training part is also completed, and my outputs are stored in this particular directory output. Okay.